So here I was, just minding my own physicsy business when suddenly a comment. Electrons are all the same because there's only one. Yeah. This idea is called the one electron universe. It's a bit of a niche idea and I very much like it, but it doesn't work because... Okay, as I was saying, it doesn't work because... Maybe the idea was not as niche as I thought it was, but yeah, it does not work because it does not. Because... Are you done now? Yeah? Okay, so the one electron universe does not work because... Okay, so the one electron universe is definitely not as niche as I thought it was. So, especially because of that, I think it would be nice to have a closer look at this one electron universe idea. And at why it can't be how our universe actually works. So, today on Fundamentally Explained, the one electron universe and why it doesn't work. Let us first try to understand the problem the one electron universe actually tries to solve. The universe is built out of, and therefore filled with, particles. Electrons, photons, neutrinos and others, and there are many of them. Approximations say that there are more or less this many electrons in the universe. Just electrons. And the fundamental properties of all these electrons are all exactly the same. Their masses are identical, their electrical charges are identical, their spins are identical, their lepton numbers are identical. This begs the question, why? Why are all these properties exactly the same? Well, modern understanding is that two particles are of the same type in the same way that two waves in a pool are the same. Their fundamental properties don't come from the waves themselves, but from the pool in which they quote-unquote live. The shape and size of the waves can differ, but properties like material and velocity are all the same and originate from the pool and the stuff that's in it. For particles, the same idea holds. Their properties come from a shared pool that we call a field. Back in the early 20th century, however, this explanation of fields was not developed yet. So, two scientists, Richard Feynman and John Wheeler, played around with the following possible solution to the problem. What if all electrons are the same because there's just one single electron? It might sound weird, but that's only because it is. It just is. Just what we know. We know there are many electrons out there. So, just one electron? How can that be? How? Just how? Well, by using everyone's favorite plot device, of course. Time travel. Yes, this was their actual idea. To understand it, let's look at how objects usually move through time in the first place. Things move from the past to the future. No shocker there, I hope. In this diagram, we indicate this as moving from left to right. The line our electron draws in this diagram is commonly called its world line, and it indicates where the electron is for each moment in time. Notice that this definition is unique. If this line indicates the present or the now, the world line crosses it only once. As a result, our world would only contain a single electron. But what if our electron could time travel? Absurd, I know, but bear with me. Time travel would mean that the electron could reverse course and move from right to left, possibly crossing the now line again. As soon as it does, there's not just one electron in the now, but two. But why only two? It can of course reverse course again, creating another electron in the world. And again. And again. And again. And again. And so on and so on. A single electron can thus appear to be multiple electrons by time traveling. By tracing the world line, however, we can see that they are all, in fact, the same single electron, with the same single mass, charge, spin, etc. Why is this idea then incorrect? Apart from the fact, of course, that time travel is just a lousy excuse to fix holes in either theories or movie scripts. Looking at you, prisoner of Azkaban. Well, to test an idea or hypothesis like this, we do what we always do with them in physics. We use experiments to check if they correspond with how the universe actually works. In the video on antimatter, which I will link at the end of this video, we saw that electric charge is conserved. You can't create or destroy it. We have never seen processes that violate this rule. This is, however, exactly where the one electron universe starts to break down. Back in our diagram, at this point in time, there's a total charge of -1, -2, -3, -7. But here it is -1, -5. In our one electron universe, charge is thus not conserved. This is specifically the case when the electron turns around in time. At those points, 2 electrons appear, which creates charge, or 2 electrons disappear, which destroys charge. That simply does not match with how nature seems to work. So the solution we found for this problem back in the antimatter video was that when the arrow of the particle's world line points back in time, it does not represent an electron, but a positron. Positrons are like electrons, but have an opposite charge. This does fix our problem. The total charge is now 0 everywhere in this diagram. In fact, this solution fixes charge conservation in any diagram, including our original one. Just pause the video if you want to check it for yourself. So, just add antimatter and all our problems are over. It sounds like a perfect fix, but it actually introduces the single biggest problem with the one electron universe. Because although antimatter and positrons definitely do exist, compared to normal matter, there is really very, very little of it. Suspiciously little, in fact. Comparatively, there's practically no antimatter to speak of. Meanwhile, in our one electron universe, in order to have our 4 electrons, we needed that same number of world line segments going forwards in time. This meant we also needed that same number of segments, plus or minus 1, going backwards in time. Our one electron universe predicts equal amounts, or almost equal amounts, of matter and antimatter. In reality, we have approximately this many electrons in the universe. So that means we should also see this many positrons around. And that is the problem. We don't. Relatively speaking, we see almost no positrons at all. The simple conclusion is thus this. If the one electron universe predicts equal amounts of matter and antimatter in the universe, which it does, and there is no significant amount of antimatter in the universe, which is also true, then the one electron universe cannot be true either. It simply does not match with what we know to be true about nature. It might work theoretically, absolutely, but that does not mean it describes the universe we live in. But that's just the way physics and science in general works. Guesses like this one, more often than not, go to die in experiments. All of this entire video is a very long-winded way to say essentially the same as Richard Feynman himself said. Remember, one of the scientists who came up with the idea of the one electron universe in the first place. I'll end this video with his own words. Try to link what he says to what you just learned. Don't forget to like and subscribe, and I'll see you next time.
If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is, it doesn't make a difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.